Hello, chemistry students. Here is the start of your Chapter 9, Section 2 notes, talking about the CHEMath section and the mole calculations section. We're going to start with the CHEMath section. This is talking about dimensional analysis, and dimensional analysis is also called the factor label method. And dimensional analysis is used to convert units. Okay, it is the system that we use to solve the problems in Chapter 7, and it's the same system we're going to continue to use to solve the problems here in Chapter 9. Okay, so this is what a dimensional analysis is. Okay, basically, dimensional analysis is going to use the units like their algebraic letters to see or to make sure they cancel or cross out, depends on what term you like to use. Okay. Dimensional analysis can be used not just in chemistry, but in many other areas of life as well. So, for example, I can never remember the distance, time, speed equation, okay? But I know that if I want to figure out my speed or distance, rate, time, to get... we'll talk about it. I've got it all confused in my head right now, so it's not going to work, okay? But dimensional analysis isn't just used in chemistry, okay? My husband, who's a nurse, used dimensional analysis. He uses dimensional analysis to figure out dosing for his patients, especially when they're using IV drips and such. So it is a way to feel confident about your calculations. So dimensional analysis uses conversion factors. Okay, a conversion factor is a ratio of equivalent or equal measurements conversion factors are like they're equal to 1. So they're like multiplying by 1. And you always use your conversion factor so that your units cancel out. So the power of a conversion factor is that it can be flipped depending upon where you need the units to be. Okay. And the whole purpose of using dimensional analysis, okay, is that it's used to prevent mistakes. So this really used to bother my fellow students in chemistry. So there were a group of us that started studying chemistry together from the time we were freshmen up through our junior and senior year. We always kind of worked on our chemistry assignments together, our homework and such, lab reports, things of that nature. And they all knew that I was not a very strong math student. I am that person that puts it in my calculator and my calculator gives me the wrong answer, okay? So they didn't ever trust like the number I got, right? I always confirmed the number I got from my calculator with somebody else to kind of confirm that I was putting it in my calculator correctly. However, they used to get mad at me because my high school chemistry teacher was really, really picky about using dimensional analysis or this factor label method. So I always had to show my work just like I'm asking you to do. So we would sometimes do a problem using dimensional analysis that would, on a whiteboard, like a whiteboard the size of my classroom, that would reach all the way across to go to a second row to get our units converted to the units we want. And I would always take the time to write that all out, okay? My friends, they were really good with their calculators. They would just start plugging numbers in their calculator. And I would tell them, based on what I heard them say, whether they were multiplying or dividing by numbers, I would tell them when they got their answer that it was wrong. And they would be like, "What do you mean? You haven't even done it yet." And I said, "Well, I've taken the time to write out all my conversion factors and see that my units are canceling, okay? And I know that what you've done, you don't have your answer in the correct units." Okay, so the purpose of using dimensional analysis, the purpose of showing your work, is that it's used to prevent mistakes. So we're going to use dimensional analysis as we do these stoichiometry problems. We're going to start by talking about some chemical calculations, and specifically we're going to focus today on mole-mole calculations. To do mole-mole calculations or any calculations that involve stoichiometry, you have to have a balanced chemical equation. So a balanced chemical equation, and we kind of looked at that already, okay, provides lots of information. If you remember, we looked at our balanced chemical equation, and remember, we interpreted our balanced chemical equations in terms of representative particles. You can interpret those balanced chemical equations in terms of moles. You can interpret this balanced chemical equation in terms of mass or weight. And you can interpret a balanced chemical equation in terms of volumes. Okay, so a balanced chemical equation really does provide us with lots of information. Because of that, our balanced chemical equation is also essential, right, which is another way of saying required, for all calculations involving reactants and products. And again, that's what we're going to be doing in this chapter, okay? We're doing stoichiometry. We're calculating the amounts of reactants or the amounts of products. So we're always going to have a balanced chemical equation, even if the problem doesn't give us one. This is important because, okay, if you know the number of moles of one substance in that balanced chemical equation, the balanced chemical equation allows you to determine, or more likely determine by calculating, okay, the number of moles of all the other substances in the reaction. So if I have my balanced chemical equation and I know the amount of one of my substances in that equation, I can figure out how much of all of the other substances I either need or would produce. So this balanced chemical equation allows for a new conversion factor. So it allows for a conversion factor called a mole ratio. Okay, so if I have a balanced chemical equation, I can write some conversion factors which are called mole ratios. Mole ratios are really important because mole ratios are our only way to convert or change from one substance to another substance. Okay, so we're going to look at some mole ratios here. with this equation I have here, this nitrogen plus hydrogen forms ammonia, a reaction that we've already written and balanced before. Okay? So, when we talk about mole ratios, what we are talking about is there are quite a few of them. Okay? Basically, we're going to relate the amounts of moles of all the different substances. So I can have a relationship about nitrogen to hydrogen. I can have a relationship about nitrogen to ammonia. And I can have a relationship about hydrogen to ammonia. Okay, so there's 3 mole ratios in this equation. If I had another product, there'd be even more mole ratios. So remember, when we're talking about interpreting our balanced equation in terms of moles, our coefficients tell us the relative numbers of moles. Okay, so that kind of red mole ratio there is that I have 1 mole of nitrogen, because my coefficient on nitrogen is 1, to 2, or as a ratio, a conversion factor, to 3 moles of hydrogen. Now again, remember, if I need to, I can flip this depending upon where I need the units to be. Okay? That blue one, right? That conversion factor. Okay, and it doesn't matter which one I put on the top and which one I put in the bottom. So 2 moles of ammonia, because my coefficient is 2, to 3 moles of hydrogen, because my coefficient on hydrogen is 3. And again, if I need to, I can flip this depending upon where I need my units to be. My last mole ratio is going to be that nitrogen to ammonia one. Again, my coefficient on nitrogen is 1, so it's 1 mole of nitrogen to 2 moles of ammonia. And again, depending upon where I need substance units, things to be, I can flip them. Now, notice something about this, right? Some of you have probably been annoyed at how much space I've been taking up, because every single time when I've been doing problems up until now, I've always included the substance. And you've probably been annoyed because you're like, you don't really need to use the substance. It's the same substance. It doesn't change. But notice what's happening here, right? I have different substances every time. If I leave those substances off, okay, like for example, if I take this red conversion factor of nitrogen and hydrogen, and I get rid of that nitrogen and hydrogen, that's not very useful for me. Okay, so what you're going to see as we talk about stoichiometry and doing these stoichiometric calculations is it's going to be very important that you have the substances written as well. You can't leave those off in your conversion factors. Okay, so take a moment to pause the video right now and find your chemistry toolkit and add, this should be the 6th tool to your chemistry toolkit, this mole ratio. And normally how people write it is they write mole ratio so they remember its name. And they write some number of moles of, normally we just kind of do an A, to some number of moles of B. The reason for using the A and the B is so that we remember that these are different substances, right? This is the only tool on your toolkit where the substances aren't the same. Okay, and again, you can make a note to yourself, right? Where do I get these numbers from? Right, these numbers come from my coefficients of my balanced equation. So again, you can take a moment to pause the video and add this tool to your chemistry toolkit. Okay, so using this new tool, this mole ratio, we can do all these stoichiometric calculations. This is the only new tool you have to learn in Chapter 9. The rest of it is using the tools you already have. So we're going to look at an example, and again, we're just going to use that same equation we've been working with, the nitrogen reacting with hydrogen to produce ammonia. And again, because these are often story problems, I like to write information underneath my equation. So in this problem, I have 3.8 moles of nitrogen. And I want to know how many moles of hydrogen I need to react with it. Okay? So I still do these problems the way we've been doing problems all throughout Chapter 7. Nothing new. I'm going to always start with my given. So my given in this case is 3.8 moles of nitrogen. Now, notice I'm going from one substance to another, and my only way to change from one substance to another is with a mole ratio. So the tool I'm going to use here is going to be a mole ratio. Now, moles of nitrogen, remember if I have to, you can write it over 1, but moles of nitrogen's in the numerator, so moles of nitrogen have to go in the denominator. And I want to convert it to moles of hydrogen, right? So I'm going to put moles of hydrogen in my numerator. My units are crossing out. I'm going to be left with units of moles of hydrogen, which is what I want, so I'm happy about that. Now, again, where do I get these numbers? This is a mole ratio, right? To get my numbers from my mole ratio, I use my coefficients from my balanced equation. So my coefficient in front of hydrogen is 3, so I put a 3 in front of moles. My coefficient in front of nitrogen is 1, so I put a 1. Now again, because you have, right, paid attention here, right, we multiply by numbers in the numerator, we divide by numbers in the denominator. So 3 times 3.8 gives me an answer of 11.4 moles of hydrogen. Now, I should always pay attention to significant figures. Right here I have 2 significant figures. So my answer should only have 2 significant figures. And the way it's written right now, it has 3. So I should rewrite my answer as 11 moles of hydrogen. So that's my answer right there. So you have a homework, which is on page 250 to do number 19. I will make a video and post a video for you on those homework corrections so that if you find that you're struggling, you can get some help. I will talk to you later.